malfunctioning of the circuit. Some defect fortunately doesn't lead to the malfunctioning of the circuit. Now, when I manufacture a chip, I have visibility of the output. So if some defect causes malfunctioning of the circuit, in that case, that is our concern. And therefore, rather than targeting the defect, because defects can be numerous, it's very difficult to model all the defects and target every defect and defect the test for that. We look at that how this defect is manifested itself as a malfunctioning of the circuit or functioning of the circuit, and whether it results into an error. So error, we define that a wrong output signal produced by the defective system. So error is an effect whose cause is some defect. So because of defect, we are getting error in the output, and now we abstract out that error, and we call that as a fault. So fault is a representation of defect at the abstracted functional level. Now, and we have, so yesterday we discussed that we need to model the faults, because now faults are the logical abstracted errors. Now, we can target each and every fault and can find a way how to uh, test that particular fault. As we had seen yesterday, that functional testing is too tough task. You cannot test functionally if the number of inputs are beyond certain numbers, maybe beyond 50, perhaps up to 50, perhaps still you may be able to manage to have exhaustive test, but after that it is not possible. And therefore you have to use some fault model, and then target these faults. So now one of the fault model that we have discussed yesterday. So fault models, if I make, in that case, this can make the analysis possible. You can analyze that whether some particular fault is there in the circuit or it is not there in the circuit. And this also gives you a quantitative measure, that how many, whatever test vector set that you have developed, how many faults it can uncover. Keep in mind, then we want to minimize the number of test vectors, because all these test vectors, when we apply to the chip, it consumes some time, and the tester time is quite precious. As I mentioned yesterday, that it cost you 5-6 rupees per second. So therefore you want to have a test vector set as compact as possible. So now the numerous defects that we had already discussed yesterday, and because of these defects, maybe the defect can be like here, the sort of the registers, or sort of like here the gate and source, or something like that, and that can be say lumped at a net in the circuit. So now we can model, like here, for example, yesterday we have seen that there is a defect in the layout over here, which can say that can bring in some say additional resistance between the source and ground. And because of that, the potential at node Z remain always ground potential, or close to ground potential, and hence it infers always a logical zero. And therefore during the operation, what it will do is this will keep on seeing the value 0 at Z. So that fault I can call as a stuck to logic 0, because Z cannot change its value from 0. And so now we had seen yesterday that we can have a fault model that can be stuck to logic 0, stuck to logic 1, right? And then, I mean, if there's no fault in that case, it would be a good line. So you can have, I mean, that we, I mean, that's how we develop the stuck at fault model, which was developed way back in 60s. And around that time, here there were only few say transistors we were able to implement on the chip, and therefore only out of many transistors, maybe if there is something goes wrong in that case, probably maybe one node might be upset and all other things may be correct, and then the developed single stack fault model was uh, was a reasonable model. Now, but the model was developed in 60s, that industry is heavily using till date, and because this fault model can give you a set of test vectors, and those set of test vectors can detect most of the multiple faults in the circuit. And as I mentioned yesterday, that about 60-70% faults it can detect, and that's good enough for the industry. And hence the single stuck at fault model survives till date. So everybody is using the stuck at fault model at least. So that means they have to generate the test for single stuck at fault. Now so, and that's why we call this fault model as a abstract fault model, or logical fault model, or you can call Boolean fault model, functional fault model, symbolic fault model. It has nothing doing with the real defect in the chip. So this is not a defect model. This uncover most of the defects that can occur in this circuit. That is the beauty of this model being very simple. And now I can quantify in my circuit. If I have n number of nets, in that case I can have at the most 2n number of faults, and I can target each and every fault to make sure that my circuit is correctly implemented or not. So whether it's a defective circuit or defect free circuit, that we decision we make based on the outcome of the stuck fault test. Keep in mind that we are using these fault models to develop the test set. So if I mean, while we are developing the test set, we assume that fault is there, and if that fault is there, in that case, can I have some input which can distinguish the output in the presence and in the absence of the fault, uh, that act as a test vector for me. So uh, so like here, we yesterday we already discussed that if there is a stuck at fault model, fault at net z, I can get a test vector that is 1 0 0. And in that case, what can happen if it is say fault free circuit? In that case, output would be 1. If it is faulty circuit, output would be 0, and therefore this particular say input 1 0 0 can act as a test vector for this. So the requirement from the test vector is that the vector should give me two different values when circuit is fault free and or circuit is faulty, so that I can make a decision whether that particular fault exists or that fault doesn't exist. And yesterday, Professor Menka already, I guess, explained you that I mean, you can there are multiple faults which needs only the same test vector, and we call them as equivalent faults. Then now if there are so that means one particular test vector can detect multiple faults, or one fault can be detected by multiple test vectors, and therefore that gives me the opportunity to optimize the number of vectors, that how many vectors I need to detect all the faults, how many minimum number of vectors I need to detect all the faults. So that's the main task all the time we have, to minimize the test time that we I mean it can incur. So the single stack fault model was the first model which was proposed way back in 60s and surviving till date. It was actually developed for the TTL circuits. TTL is transistor level logic circuit, that was based on BJT. But 70s onwards, we have shifted to from TTL to NMOS, then CMOS, and in CMOS, NMOS. Again, people looked at that whether the single stack fault model still work for CMOS or NMOS kind of circuitry or not, and they figured out that here this can pretty much cover all kind of defects which can occur uh, in the CMOS circuits, and hence these were like here extensively used for CMOS circuits as well. There are couple of faults which or defects which perhaps the single stack fault model cannot uncover in CMOS circuits, and for that I mean, we have added some additional fault model at the transistor level. Those are transistor open and transistor short. They, I mean, you have to you need to have develop the different test vector to see whether some particular transistor is open or some particular transistor is short. These are the faults which may need two vectors to test, and hence I mean that was not covered by the single stack fault model. So that those are the augmentation. So I mean in TTL, single stack fault model was enough. It could uncover all the transistor defects, the or most of the transistor defects that can that may occur while you are manufacturing the transistors. However, in CMOS, this can uncover most of the defects other than the transistor open and transistor short. All other defects can be uncovered by the single stack fault model. But then we use the additional vectors for testing whether transistors are open or transistors are short. Then these are the logical say uh, defects or logical faults. So that means here, no matter how long I keep in input, here the if a fault if a net in the circuit is stuck at 0, it will continue to stay at logical 0. uh, However, that perhaps may not occur all the time. There are some nodes wherein you if you provide enough time, in that case those points can change, or those nets can change their value from 0 to 1, but then they are slow. So that means they don't have a logical defect or logical fault, because if I provide enough time, in that case that not that particular net, like for example here if I say z, so if I give enough time, in that case it can change from 0 to 1 or 1 to 0. However, in a given clock period time, perhaps it may or may not be able to change that. And those are the defects that we are getting can upset the timing of the circuitry. So that means your circuit may not operate at the clock rate at which you want to operate it, and therefore some additional fault models were developed say test such kind of performance oriented faults. So these are the faults which are affecting the performance of the circuit. So like here, for example, I design a circuit for to operate at 4 gigahertz. Perhaps it may not operate at 4 gigahertz, it can operate at 2 gigahertz, it can operate at 1 gigahertz, and so on and so forth. So so those fault models are we call as the delay fault model. There are two different models which have been proposed, and if time permits and your schedule permits, perhaps or maybe someone else might be covering this delay faults. So the it has a transition delay fault model and path delay fault model. Path delay fault model is more of say academic purposes, because the number of paths in a circuit are too large, so we cannot target all the paths which are possible in the circuit to test. However, transition fault model is pretty much similar to the stuck-at fault model, wherein every net we say that whether that net is able to change its value from 0 to 1 or 1 to 0 during the clock period time, and therefore the number of transition delay fault would be equal to the number of stuck-at faults we have, and that is equal to twice the number of nets that we have in the circuit. So this number is small enough so that we can develop the test vector and test these in a practical circuit. And most of the companies are testing their circuit using the transition delay fault model. Path delay fault model is too expensive to test, and most of the companies don't go for the transition delay model, path delay fault model. Though there is a scheme between the transition delay and path delay that we call as segment delay model. So rather than neither we use a single node nor we use the complete path, but then we use a small segment of the circuit. So that's the way we go. Then there are I mean faults which there are other elements in this circuit that we have are so we can have logical elements, like logical circuits. We can have adder, subtractor, multiplier, and all such kind of arithmetic circuits. Or we can have like here the ALU, wherein you can do and, or, XOR, XNOR. Or we we can have memory. Like for example, if you want to implement a state machine, you mandatorily you need some kind of memory elements. So if there's a memory element, in that case, the one way to deal with the memory element, because memory is also constructed using the transistors. Actually, it's like here you can say that the back-to-back connected inverter makes a memory cell. But now so either we should test this as a transistor fault using the transistor fault model, because then now I have inverter, and then these are every inverter have two transistors, so there are 4 transistors. I can check those 4 transistors. Or it's a regular array, and then we can develop another functional fault model for the memories, and that we will discuss today in today's talk. So those are so then we because of the regular structure of memory, we have developed another functional fault model for the memory. Then there are fault models that we are using for another kind of regular structures that we have, like for example programmable logic array, PLA or PAL, which are very regular in nature, wherein you have some and or gates, and then they are reconfigurable. So there are say switches in between, which can provide you the connectivity. And then looking at their functionality, the newer fault models were developed for that. One is of course the stuck at fault model that we were using earlier. Same thing, one can extend, but then the cross point or bridging kind of fault that can also occur, and which were used in that. Similar kind of things are also hold good for the FPGA kind of regular structures. Then coming to the another very important component in the circuit, that is processor. Processor provides you the abstraction of the lot of logic. So like if I write a program, in that case program I can deliver to the processor through the instructions, and then the instruction will tell it that here add two numbers a and b, and then write the result into c. So c equal to a plus b, we provide. This does all these kind of say operations. That operation consists of bringing instruction from memory to the processor, understanding that instruction, doing the arithmetic or logical manipulation, and then write back the result to the destination. So these are the functionalities of the instruction. Now one way to test processor is that like here I can consider that as a any other sequential circuit, and then test the circuit as a sequential circuit. However, because it provides me abstraction, I can also test using its own functionality. And initially in early 80s or during 80s, people have developed the functional fault model for processor. That means here using the functional way, or using the functional instructions, you try to test processor whether the processor is acting or has been implemented correctly or not. That is like was pretty much very close to or similar to the verification of a circuit, and with limited way or constraint way. Later on people have developed the approaches to mix the structural test of the device. That is structural test means here testing of each the structure, whether that structure is implemented correctly or not. And that we can test by testing every stuck at fault at every net, because net represent the structure of the circuit. So whether all the nets are healthy or they are unhealthy, right? So now the way was to somehow combine the structural test plus the functional test, and that most of the that is called as instruction based test of the processors, or software based test of the processor. So that's like here became quite popular and quite common lately. So that's the another kind of fault model people are using. Maybe if time permits, we can discuss a little bit about this. And finally, the if you design an SoC has whole lot of digital circuitry that may consume something several billions of transistors. However, a small pass portion on the chip would be analog circuits. And now these analog circuits, like here you have ADC, DAC, and then some inputs coming from the sensors or something like that. Now how to test the analog circuits, that is another challenging problem. We have done pretty well for all the testing of the digital circuitry. However, the test of analog circuit is still in infancy. If anybody has an interest, this is another interesting problem to target. So people say that here the 10% portion of the circuit is analog circuit. However, we are spending 80-90% time in testing that analog circuit, because the analog circuit test is pretty much like here the specification based test, or that is like a verification of a circuit. So that's the too expensive exercise. Maybe I can skip this part. So these are the various fault models that we have. I mean, we have discussed. If we can go more elaborate way in say uh, due course of time. Um, so now here come back to the today's topic, that is memory testing. Memory, as you know, is a regular structure, and if you look at the SOC today, the 90% area of an SOC is consumed by memory. Over the years, what has happened, I mean, people say that in 60s, I mean, in 80s, 90s, the designers have had a lot of concept, and they were asking technology colleagues that if you give me some more transistors, I will give you wonderful performance. And the technology colleagues did not have uh, additional transistors to offer you. However, today we have whole lot of transistors available. So technology colleagues say that here we have a lot of transistors. Do you have any way to use those transistors? So now we are running out of ideas, and however the technology is continuing to offer us the additional transistors. So what to do with those transistors? And the simplest way is to use them, or to extend the memory that you are using. So now here memory is increasing day by day in the circuit. Even if you look at the microprocessor, then there is a whole lot of memory components involved inside the design, that can do whole lot of predictions, etc., etc. So I mean, 90% area of the SOC is consumed by the memory, and therefore memory is very say interesting design. And the if 80-90% area is consumed by that, in that case any saving on the testing of that 80-90% area would be really result into a larger saving. And now therefore people started to look at that, I mean, is there any different way of testing the memory, rather than going for stuck at 0 or stuck at 1 fault in the memory cell. So because this is a regular array and it has very limited functionality, that's very important. Say if I look at the random logic, I don't know the functionality of the circuit. Every circuit has different functionality. If I implement microprocessor uh, provide me some kind of abstraction, but then that is still vast. But memory can provide me very say limited functionality. What that limited functionality is, that it can store value 0, it can store value 1. If I want to write onto this, in that case you can change it from 0 to 1, or you can change it from 1 to 0, right? These are the total functionality it provides. So then can I make use of that to minimize the time required to test that particular circuit? See, as I said earlier, and again I am saying that the time of testing is very very important, because when you are putting your circuit on tester, it costs you something 5 to 6 rupees per second, and hence we want to minimize the amount of time that you need. So in a memory circuit, what you have storage cell. Those storage cells are say um, uh, I mean placed in a matrix format, so in two dimension, x and y. So that means in rows and columns. You when you are writing to these memory cells, in that case you have to excite one particular row, and then you either write to this, or you read from this. If you are reading, in that case you sense, I mean use the sense amplifier. That sense amplifier can sense the difference between the bit and bit bar line, and make a decision whether the stored value is 0 or stored value is 1. So this is how memory works. So it's a very regular structured way of designing the circuit, which is doing very limited kind of functionality. So now now these are little bit older data. So if, let's say that here, if my memory size is uh, um, uh, some number n bits I have in the circuit. So and the I mean I forgot what was the frequency which was used, something few megahertz. So now this says that because this is the regular array, if I can test this particular memory by simply doing some task with with a memory element. That means, because it does the limited functionality, storing 0, storing 1, transition from 0 to 1 or 1 to 0. These are the operations it does. Now with every memory element, if I can check all these operations, then I can conclude that that particular element is good, right? Whenever when I store 0, it is storing 0. How I get to know that whether it is it keep storing 0? By checking, first I write 0, and after some time if I check whether it is returning the 0 or not. If it is returning 0, in that case that element is good. If I write 1, and after a while if I check whether it returns the 1 or not. If it returns 1, in that case I can say that here, yeah, it has retentivity of 1. Then I have I write 0, and then after a while I will check 1. I change it to 1, and then after a while if I check with what is the value it is storing. So if it stores 1, that means here my transition went through. Otherwise I can say it is failed. So that transition also I can check. Or first I write 1, and after that I will change that 1 to 0, and then after a while I will check what value it is storing. If it is storing 0, in that case I can say my transition from 1 to 0 also happens. And these are the limited functionalities, right? It needs to have. So if I can do a limited set of operation with a cell to identify whether that particular cell is good or cell is not good. And now let's say that here the number of operations are just proportional to the number of cells that I have, or number of operations are proportional to n square, or number of operations are proportional to n log n, or number of operations are proportional to n raised to the power 3 by 2. And we will see that here, when you get n when you get n log n, and why they are important, and which is doable and which is not doable. So any scheme that you are devising that may have complexity of n, so that means n operations you need to do to carry out, or for testing the entire memory system that you have. N log n is the n is the number of memory elements you have, and if you need to do log of n operation with every element, in that case you may the complexity would be n log n. And if I have n number of elements and you are doing n operation with every n element, in that case the complexity of this would be n multiplied by n, that is n square. Now you can see the difference, that's very important. Let's say that here I have 1 MB memory, so that means n is my 1 million bits, right? So n is 1 million bits, and if I run on, this for this data I forgot what was the frequency of operation we have used. But let's say that here for some frequency it takes 0.06 seconds time. If I go for n log n, in that case this will become 1 second. That is still okay, doable. If I go for n raised to the power 3 by 2, so that means the for n operations, every say bit, if I need to do root n operation, in that case my complexity is n raised to the power 3 by 2 or n raised to the power 1.5. Then this becomes 64 seconds. That is still doable. Now if it then if this is n square, then this goes to 18 hours. That is not doable, right? This is for 1 MB. Now if you go for say 1 GB, 1 GB memory, now you have you in your systems 8 GB or 16 GB or something like that, right? So now you see that here if it is 1 GB, in that case, for if complexity is n, in that case it will take 64 seconds. That is large, but still doable. It is about a minute. N log n, it is about 2000 seconds. If it is n raised to the power 3 by 2, in that case this will be about 500 hours. So long, several days. And if it is n square, in that case this would be few million hours, right? That's not doable, not practical. So that means anything, whatever we want to do, must have the complexity as n. So that means here the number of operations that I am doing with each and every cell should be constant, should not vary with or should not change with the size of memory. That is the lesson that we can draw from this particular table, or these numbers that those have been calculated. So now I in systems I can have say uh, what we as RAM, or we can have DRAM, static random access memory or dynamic random access memory. Static and dynamic random static random access memory we are using for caches in the processor. L1 cache, L2 cache, L3 cache. Generally in your systems, L1 cache is few KB, L2 cache is like about 500 KB or around MB, and then the L3 cache is like 4 MB or 2 MB or something like that. So that's the kind of size that we have in as RAMs. Whereas the DRAM is the dynamic random access memory, wherein you are storing data as a charge on a single transistor. And because that's very compact, and hence we can have large amount of memory available, and the so the DRAM is size is something like here say few GBs. So there are some faults which you can get only in the SRAM. Those are like your uh, so like for example, open circuited pull-up devices. Pull-up device, the transistor that you are using can be opened, or transistor itself can go open. Excessive bit line coupling capacitance. There are bit line and bit bar lines, and you are running those bit and bit line lines all through the circuit. When you are running these bit and bit bar line all through the circuit, it is they are high capacitance lines, and if high capacitance lines, if you are running close to each other, in that case there can be coupling between these capacitive lines, and because of that coupling, the value on one start to affect the value on the another one, and that we call as the say coupling faults. So when we want to model the faults, in that case we can model you, assuming that my memory is a black box, that is like a that the task of that is to store the value. If I want to store 0, it stores 0. Want to store 1, it stores 1. And want to change from 0 to 1 or 1 to 0, in that case it will do that. So now I can have a behavioral model that we can represent using a state machine. uh, so that is one model that one can have. But then now here state machine, if I develop for all the cells that we can have, now that would be a humongous, and would become intractable. uh, Functional fault model that we can use. So the functional fault model means we can use simply the high level functionality of the circuit, wherein you can say that the cells can store 0, can store 1, or can write change from 0 to 1 or 1 to 0. So that we call as the gray box model, because we know something about the memory inside, how this is constructed, and how they are placed with each other. And this model is mostly used in all the memory level testing. And the other models that we have, I mean, I have already explained you that regular stacked or kind of fault model that you can use, and can consider that as a say traditional random logic device, and can test using that. So in abstract sense, if I want to develop a functional fault model, in that case, in abstract sense, you can say that I have a memory cell array. That array is arranged in 2 dimension. In 2 dimension, I to point out one particular memory location. First, it we receive the address from the outside. That address has to be stored somewhere in the address latches, and then that has to be supplied to the column decoder and row decoder. You have to identify that your cell falls in which row and which column. So column decoder will decode. So the column decoder is a combinational logic, row decoder is a combinational logic. Only the memory cells are the storage cells that we have. And now from this one, if you want to, I mean, if you remember how the memory system works, in that case, uh, you when you want to read or write, in SRAM, you have say bit and bit bar line. When you pre-charge those bit and bit bar line, and then after that, if you want to read, you have to let them discharge. One of the line would be discharged, and then when the difference between you have to sense the difference between bit and bit bar line, and then by using a sense amplifier, and make a decision whether it is storing value 0 or value 1. This is what we do in SRAM. However, in DRAM, what happens that we are storing the value of 0 or 1 in the form of a charge, and then if you keep on reading or that particular cell, in that case that charge may keep on reducing, and now after a while perhaps it may the potential drops below certain value, and then you may start to infer from infer 0 instead of 1, and therefore those kind of memory cells, those generally we have in DRAM, we need to refresh periodically. So that there is something called as a refresh cycle. So after some time, periodically you have to read those values and write it back there. So those are the called as the refresh cycle. So you have to have a refresh logic that refreshes this periodically. So this is how the memory is organized, and then this particular model is so we use as I said, this is gray box model. So that means here I am using an abstracted information from the memory system, not looking at individual transistors, that how the transistors is behaving in that particular system. So out of this I can carve out a simplistic model. Simplistic model says that here there is a address decoder. I am supplying the address to this. Address decoder will decode the address, that is row address and column address, that will enable one particular memory cell, and then this particular memory cell you can read or you can write. So it can provide you the data if you are say reading this, or the data can be written to that particular memory location during the write time. So this is the simplistic model that I can use. Now in this model, functionally what can go wrong, and those kind of things that we have to abstract out. Now what can happen? A memory cell may, like here a transistor net point or netlist can stuck to logic 0 or stuck to logic 1 due to different reasons. Now when transistor can netlist can stuck to logic 0 or logic 1, in the similar way a memory cell may also stuck to logic 0 or logic 1. It may store 0, but then it may not store 1. It can only store logic 0. So a cell can stuck to a logic 0, or that can stuck to logic 1. That simply mean that if it is stuck to logic 0, that means here if you want to write 1 on that particular cell, this won't accept that. So it won't write 1 to be written to that. There may be numerous reasons why that can happen. Or this can a cell can stuck to logic 1 if it is so, and cannot change to logic 0. So that's the one very simplistic kind of fault model I can use, is that we is still call as a stuck fault model. So I can use that a complete cell like here in SRAM, that is a back to back connected inverter, right, along with the excess transistors. So the entire cell here you can say that here it can stuck to logic 0 or logic 1. So if there are n number of storage cell I have, in that case there can be 2n number of stuck at faults, right? I believe everybody would be agree onto this. Then there can be a possibility that the cell is not stuck to logic 0 or logic 1. However, this may possible that if I want to change from 0 to 1, it may not change from 0 to 1 within the given amount of time. However, so that we call as a transition fault. So this may not accept transitions. This doesn't mean that if I provide that the input infinitely long, at some point in time it will transit from 0 to 1. However, in the short period of time in which your circuit is operating, see, the aim of the testing is to check whether your circuit works correctly when you want to use that functionally in the field. Functionally in the field, that means you're with the rated clock that you are using. So if I'm using a circuit or operating a circuit at 1 gigahertz, in that case within the 1 nanoseconds time it should take some action, right? So that means if I'm changing from 0 to 1, in that case that change should happen well within 1 nanoseconds. And if some cell is faulty, in that case that may not happen in 1 nanosecond. But if you give 100 nanosecond, in that case here perhaps this can change from 0 to 1. So there can be a fault while it is transiting from one logical value to the another logical value. This may possible that this may not transit from or slow to change from 0 to 1, but this may change fast from 1 to 0. So the transition can be the rising transition or can be falling transition. So that means maybe 0 to 1 or 1 to 0, right? So if there are n storage element I have, in that case how many faults I can have which are of transition type? Two faults. One is the transition from 0 to 1, another is from 1 to 0. So there are 2n faults, 2n stuck at faults we have, 2n transition faults we can have. Then third one is also important, that if there is a cell, because these cells are close to each other and then they are storing, and there is there is a possibility of capacitive coupling between the two cells. If there is a capacitive coupling, in that case change in one cell may start to affect the change in the another cell. That's where the problem start to occur. Now theoretically you can say that any particular cell in a circuit can start to affect the any other cell, right? So theoretically these kind of say the coupling faults can be very large in number, because every cell can affect the every other cell. That's possible. However, physically it doesn't happen. And that's where this n square and n log and all those complexities start to come into picture. Because here if I say coupling, one cell can be coupled with any other cell in the circuit. In that case, in order to test that particular fault in a cell, what I need to change the value in all other cells and see that what is the impact on this particular cell, right? And that needs n number of tests to be applied per cell basis. And now for n number of cells, I need n square number of tests that has to be applied, and that is not doable. So coupling faults that can, theoretically any cell can be coupled with any other cell. However, that doesn't happen practically, because this is a physical coupling. Now in the physical coupling, only you can have coupling with your neighboring cells. Neighboring cells means the cell which is in your vicinity. So you can have a cell like there can be four cell in your vicinity. That means one is left, another right, top, up and down. So there are four cells which can directly impact or this particular cell. And so if I assume those only these four cells, a immediate cell, in that case I need to check for all these four change in any one of these four cells, and hence the number of operations that I need to do with every cell is constant, 4. So that is again doable, right? Stacked fault, you know that these are 2n. This transitional fault, there are 2n. Coupling fault, now if I look at only the neighboring cells, in that case this will become 4n. Then so that is again here proportional to n. Now another very important kind of faults, and these are really people say pain in the neck. So that sometimes some particular pattern in the neighborhood of a cell, like see, when all the input in the vicinity of a cell, if all are 1, in that case this particular cell is likely to flip to 1. This may not have one-to-one coupling, but a pattern around in the surrounding of that particular cell can potentially change or upset that particular cell, and that we call as neighborhood pattern sensitive fault. So these are the simplistic or reduced fault model that we can have, reduced functional fault model that we can have. Now this, except this NPSF, neighborhood pattern sensitive faults, others are like here proportional to n, and if they are proportional to n, in that case that is very much doable by a systematic algorithm that we can develop for this.
Hello, sir.
Yes.
If you want, we can have a 5 minutes water break.
Yeah, that's fine. Maybe we can have 5 minutes break.
Okay, sir. Thank you.
I really don't need, but that can give break to the attendees.
Okay, sir. Thank you. So
Okay,
let's have
so
a five
maybe
minutes
we'll
break.
reconvene after just after 5 minutes.
Yeah, thank you, sir. Hello, sir. Can we restart?
Yeah, sure.
So there is a question in the chat box, sir. Mr. Sai Kumar is asking what is the difference between NPSF and CF? That is not clear to him.
Yeah. So, am I audible?
Yes, sir. Yes, sir.
So, CF is a fault that tells you that whether this particular cell, say let's say the cell X, is coupled with cell Y. Y can be any cell in the surrounding. And I'm in this case, I'm talking about one cell at a time. That one cell, whether it is coupled with the left cell or the right cell or the top cell or the bottom cell. One cell at a time. So this is 1-to-1. However, NPSF says that it is not coupled with one, but so in a way you can say that this is like a more generalization of coupling faults, that if there is some pattern in the your near vicinity, say for example, if all your neighboring cell in your neighborhood there are four cells like your top bottom say left right, if all are holding value 0, in that case this cell X is also likely to flip its value to 0 if it is not 0. That is called as pattern sensitive, because this is sensitive to a pattern. Or this may possible that if the left and right cell are 0 0 and top and bottom cells are 1 1, in that case that kind of flipping can happen. So that is like a sensitive to a pattern that you find in your near vicinity. That's the difference between. So now in pattern sensitive, first thing is how large the neighborhood we should see. And then now let's say that if I see all four cell in my neighborhood,
Sir,
top
your
bottom left right, then there can be 16 different patterns which are possible in those, and I may need to check for all 16 patterns. Then if I expand this neighborhood, not only your neighbor but then your neighbor to neighbor, so in that case I can say consider the 8 cells which are like a one row up, one row down, one column left, one column right. So those are the 8 cells, and if I go for the 8 cell, in that case I have to check for all 256 patterns. Those are possible, right? That is the pain, that now you need to have very large number of possibilities which can upset this particular cell. Is it clear? I hope it is, but not, then maybe you can write, we can come back again.
yes, sir.
So now how to test this? So find out the test condition. So in reality, what happens if I can make a stay say model of a cell? What happens in cell? Cell can have only two states, right? Either it is holding 0 or it is holding 1. So that means it can hold pointer option. So either it can be the state 0 as 0, or this can be state as 1. Now if it is in state as 0, that means it is holding value 0, and if I write again 0 in this case, again it will stay in the same state. If I write 1 in that case, it will go to the state S1. In state S1, if again I will write 1 in that case, it will continue to stay in the same state. Otherwise, if I write 0 in that case, it will come back to state S0. This is the write behavior of a cell. Now, if there is a stuck at 0 fault, it is in state S0. When I write W0, write 0, it will continue to stay in the same state. But if I write 1, also it is also continue to stay in state S0. So that would be the model of a faulty machine or faulty cell. This is the model of a good good cell. However, if there is stuck at 1 fault in that case, it is in powers up in state S1, and when I am writing 1 in that case, this will continue to stay in state S1. But when I write 0 in that case, this will go back into again go back into state S1 rather than going to state S0. So these are the I can model that say the two state machines out of it. Now if I want to develop the test for this, right? So I represent this as for all cells that can stay. This faulty cell can stay with logic 0, or that can stay with logic 1, and that can happen with every cell. Now how do I test for this? What can be the test? That if it is in state as 0, and if I write 0 into this and read this, in both cases, whether this is faulty or fault free, it will behave exactly in the same way, right? Is there any way to distinguish whether it's a faulty cell or fault free cell? No, right? Then what can be the test? It has to be in state as 0, and if I apply or write 1 in that case, in good cell it's supposed to go into state S1. However, in bad cell it will go back again into the same state as 0, and therefore if I observe the state after this write operation, write 1, in that case I should be able to distinguish whether that particular cell has stuck at 0 fault or not, right? So that means what I need to do is I have to write I have to make sure that my cell is in state as 0, so that I can achieve by writing 0 in that, and then we write 1 and then check whether the cell is retaining the or cell has that value 0 or 1. Good cells should have value 1, bad cells should have value 0. Similar way, you can obtain a test for that can distinguish faulty and fault free output for stuck at 1. Stuck at 1, if I in a cell, if I write 1 in that case, both faulty and fault free cells will give me the same answer. However, in say if I write if I make sure that cell is in state as 1, and then if I write 0, in that case faulty cell will remain in the same state as 1. However, the fault free cell should have gone to state as 0, and that will will distinguish whether the fault is testable or not. Similar way, for the transition faults, we can say that a cell failed to make a transition from 0 to 1 or 1 to 0. And so now here what can be the test condition? The earlier for the stuck at fault, the test condition is for each cell you read say A with value 0, or read A with value 1 after writing 0 or 1. Here each cell must have an either rising transition or falling transition, and read each time. So now say if it fails to transit from 0 to 1, right, it fails to transit from 0 to 1. In that case, when it is in state as 0, when you are writing 0, it will continue to stay in state 0. But it when you write 1, in that case it may not go in state as 1, it may continue to stay in state as 0. However, if it is in state as 1, in that case it can go when we are writing 1, in that case it will go to state as 1. But when you write 0, in that case this can transit to state as 0. So this we call as the transition fault. This rising arrow will say that here fault on the rising transition. Rising transition means from when it goes from 0 to 1, and then what it says that this will continue to stay at the logic 0 state. So these are the state machines that can tell you that what I need to check for, or test for this. Coupling faults. Coupling fault, as I said, that here there is a coupling between one cell to, I mean when we are in simplistic model, we are considering coupling of one cell with the another cell. So a transition on bit j or cell j causes unwarranted change in bit I. That's so now here the bit I or cell I we call as victim, and the bit j or cell j we call as a aggressor, because change in the any change in the aggressor bring in unwarranted change in the victim cell. Here we are only looking at the coupling between the two cells, but this can be the k coupling. That means here one cell can be coupled with the k number of neighboring cells, or something like that, but then that will become more and more complex. Now this coupling can bring in three kind of effects. One is inversion and idempotent coupling. Or it can be the bridging or state coupling faults, and dynamic coupling. So I'll come to this point. If there are two cells, I don't need to go through this state transition diagram. You will see that this is the state transition diagram, which says that if both of the cell, this as 0 0 means here both of the cells are in 0 0 state. As 0 1 is both of the one cell is in state 0, another cell is in state 1, and so on and so forth. So this is the correct diagram of a given of two cells, how they are operating when you are reading and writing those cells. However, if there is a say ith cell, first is ith cell, second is jth cell. So now when you are writing into jth cell, in that case writing 1 into jth cell, in that case this will go from 0 0 to 0 1. However, if on the rising transition of so you can see that state transitions of two good cell, I and j. So when you are writing 1, in that case it has to go to the state as 0. Now when I change the ith no jth cell, when I change jth cell, in that case ith cell is also getting upsetted. So what is happening, that when there is a transition on jth cell, ith cell upset. So transition on jth cell, that means this transition, the transition in the good cell was this one. When I am transiting the jth from this state 0 to 1, this also make or upset or the flip the value of ith cell. So this arrow, up arrow, says that there is a transition on, rising transition on the jth cell will flip the value in the ith cell. So that means the transition must have been from here S00 to S01, because ith cell will remain in state 0, whereas the jth cell should have been changed to state 1. However, what happens is that the when with the transition on jth cell, there is a transition on ith cell. So that means here, now rather than going through this transition, this will start to go from this to this one. In the similar way, so there was another transition, that when it is in S10 state, that means here ith cell is 1 and jth cell is 0. And when I go from jth cell, so the transition was this one, this transition. It is in S10, this should go to S11. Now what will happen, that rather than going from here to here, this will go over here, because the value of ith cell will also flip. So this uh, uh, give you the inversion, right? So it says that here, when I make a transition on one cell, this will invert the value in the another cell. So inversion. uh, I guess you understood that when I am changing the value in ith jth cell, there is a change in the value of ith cell. That is, and that's how we are representing this. When there is a rising transition on ith cell, there is a inversion. No, when rising transition is there on jth cell, there will be a inversion on ith cell. That is inversion type of the decoupling fault. Uh, so now in the similar way, there's another kind of fault. Sorry, I forgot to have that. That is called as idempotent. Idempotent coupling fault means that for a rising transition or falling transition on jth cell, ith cell will have some fixed value, either 0 or 1. So that means whenever there is a say flip in this one, so this transition may be the same. But however, whenever there is a transition from S10 state, that means your ith cell is holding 1, jth cell is holding 0, and now when jth cell is going to change to 1, in that case this will also make the ith cell to 0. uh, just a minute. Uh, sorry. So now in I in inversion fault, what happens is that with the change in J cell, the ith cell will flip its value. If it is 0, then it become 1, 1, then it is 0. However, in idempotent, it can change to only one value. So this transition perhaps may like here, for example, if it becomes 0, in that case, this transition will remain same. However, this transition which is going when it is in state S10, S10 means the ith cell is in holding 1, jth cell is holding 0, and then when you want to write 1 in jth cell, in that case, this ideally this should go to state S11, and in that case both will hold value 1. However, now when there is a idempotent fault, in that case this can go from state S10 to S01. So this transition will change to this particular transition, that we refer as like here in this case I'm referring in inversion. I'm referring that there is a transition on ith cell, there it would be flip in the jth cell. Now in place of this flip here, we give 0 or 1 in the here the what would be the outcome, or what would be the impact on ith cell. So first is what activity happens on jth cell and how it is impacting on the ith cell. Keep in mind, ith cell is a victim cell, jth cell is a aggressor cell, which say uh, change the value in ith cell. Now the how I should test these particular faults. That's the major concern. Now we have seen, we have stuck at faults, we have the transition faults. First, let's look at the stuck at and transition faults, how it behaves. So in stuck at case, we have looked at that from this state machine, this change to either this state machine or this state machine. What shall I need to do? With every say cell, what I need to do? If I want to check whether this is stuck into logic 0 or not, what shall I do? So yeah, oh sorry, you do not have access to top. Yeah, so now what we can do is we can uh, march, or we, I mean it's an array. Sorry, I could have made this diagram. So you can go from the cell 0 to cell 1, write 0 to the cell. So what I from this one you can see, right? To test this particular whether this state machine is there or this state machine is there, how do I test? I write 0 here, I write 0 over here, then I do the transition from 0 to 1. So that means we'll write 1 and check, read this value, whether this value is 0 or value is 1. If value is 1, in that case, I mean, it is this machine. If value is 0, in that case, this is this machine, and therefore this is a faulty machine. That means this has a stuck at 0 fault. So that's what it does. First, you write on each and every cell, write 0. You can change, you can take any order of addressing, but you have to write in all. First you write 0 in 0th cell, first cell, second cell, third cell, and up to n minus 1. Then what you do? because I want to do this with the complete memory cell, then I write 0, right? So write 0 means you are here. I have written 0, so this should be, if it is this faulty, in that case this would be in this state. This faulty, in that case this would, I mean, this is not faulty or faulty, this should be in this state. If it is stuck at 0 fault, in that case this is also in this state. If it is stuck at 1, in that case this may not be in the same state, because this cannot write 0. And now what I can do, I can read this first. So first I write 0 everywhere. All blocks, all cells I will write 0, 0, 0. Now I will come back and do what? I will read what is written over there, whether it is 0 or not. If I can read 0, that means what I can say, if I am reading 0, I have written 0 and reading 0, right? At least I can say that this is not this machine, right? So that means at least I can say that this machine did not get any, I mean, did not have stuck at 0 fault. No, sorry, stuck at 1 fault, because it is able to store 0 value, right? So it is not stuck at 1. I can rule out that possibility if I can read the value 0. So I will go back and read. So read value 0 in one order of address. So first I have written 0 everywhere. Now I will start from cell 0. First I will read 0. Read 0 will ascertain whether there is a stuck at 1 fault or not. Right? Then I will change that state. After reading, I can change that state by writing 1 to as 1. Now this machine won't change the state. This machine can change the state, right? So everywhere, first I will this says that for all cells 0 to n minus 1, you first read the value of cell. Expected value is 0. If it is 0, in that case that cell is at least does not have stuck at 0 fault. If it is no, it does not have stuck at 1 fault, and then you write 1 to that. This symbol, the rising symbol here says that here I take addressing from 0 to n minus 1. Do two operations with this. First I will write 0, then I will first I will read 0. Read 0 means I will read that value of the cell and check against value 0 whether it is holding value 0 or not. And again I am reiterating that this will rule out the possibility of, if I am able to read 0, that means here it will rule out the possibility of having stuck at 1 fault in that particular cell. Now I will write 1 and keep going until the end. Now when I reach to the end, I will come back from there. Maybe order, I'll let you know that why that order is important. Order is important sometimes. Let's say that here I will come in the reverse order and do the following. I will read this value 1, and first forget about this write 0. I will do only one thing, that in the reverse order, if I move and I see from n minus 1 to 0 and see that whether my cell is holding the 1 or not, because I have written 1. If it is not holding 1, that means it has stuck at 0 fault. So it can check the stuck at 0 fault. You got this point?
Yes, sir.
So what it does is that first you write 0 everywhere, then next round you come and read the whatever value is written in every cell, and if you read the compare against 0, if that comparison succeed, that means that cell at least does not have stuck at fault. Then you write value 1 because you want to check for stuck at 0. Write 1, and then this way you keep on doing until the last cell. Then from the last cell again you come back, and then you are reading what value it is storing. If it is storing value 1, in that case it doesn't have stuck at 0 fault, because I had written value 1, and if I am able to read value 1, in that case there is no stuck at fault model, no stuck at fault exists in the circuit. So now I can be able to uncover the stuck at 0 as well as stuck at 1, or can test stuck at 0 and stuck at 1 by running the following test. In first time, I am going from the cell 0 to cell n minus 1 in any order. I am doing the all and traversal and writing 0 everywhere. That we call initialization. That is we call as march that is march 0, or we call march, because like in say army, people are marching from one point to another point. So here we are marching this 0 or 1, starting from one cell to the all the way to the last cell, or from last cell to all the way to the first cell. So this first we do this marching in any order, either from 0 to n minus 1 or from n minus 1 to 0. Although the any other order is also fine, but if you are doing in any other order, in that case, how you make sure that you have covered all the cells. So easy way is either you go from 0 to n minus 1 or from n minus 1 to 0, and write 0 everywhere. That is the initialization step we call as march 0. Then in march 1, we do two operations with every cell in the rising order of address. So we write 0, read the value and compare against 0, that we call as R0. This R0 means we are reading and then comparing against 0 value. If that passes, that means that particular cell does not have stuck at 1 fault. And at the same time, we write 1 into that particular cell and go all the way to n minus 1 cell. Right? So I do 2 scan of the entire memory array. In first array, first scan we do only one operation. In second scan I did 2 operations, one is reading and another is writing. Third time, so first march 1 ascertain that whether the some cell have stuck at 1 fault or not. Third time I will go back and from last cell go all the way to the first cell and say that check whether the element is holding that value 1 or not. Therefore I will read that particular cell, and if you read that particular cell, in that case I have to check against the one. If the check succeed, in that case you can say that this does not have stuck at 0 fault. If this check fails, in that case you can say that here that particular cell has stuck at 0 fault. So now in this case, first forget about this W0. Now I am doing the three marches, one march in any order 0 to n minus 1 or n minus 1 to 0, wherein I am doing one operation, writing 0 everywhere. Second march I am doing this in increasing order of address, though it is not important to do in increasing order, but the march M1 and M2 should be in the reverse order. So March M1, I am going in the forward direction 0 to n minus 1. I am doing two operations, one read and one write. And in March 3, I'll go in the reverse direction of March M1 and read whether it is storing the value 1 or not. For a while you forget about this W0. So in that case, how many read write operations we are doing with every cell? First march I am doing n number of write operations. Second scan we are doing two operations, one read one write. And in the third march we are doing doing one operation, one read operation. And therefore with every cell I am doing 4 operations. So the complexity of this algorithm would be 4n, because with every cell uh, I have to uh, uh, every cell you have to do the n number of operations. I mean 4 operations, and there are n cells. In that case the complexity would be 4n, that is the constant. And this can uncover all stuck at 0 faults, stuck at 1 faults. Need 4n operations to uncover stuck at 0 and stuck at 1 faults. Now so like this we can have sorry yeah maybe it's already 11 o'clock. So I guess I gave you an idea that how we can test the stuck at faults. So 4n kind of algorithm is good enough to test all stuck at faults. It can, if any cell is faulty that has stuck at 0 or stuck at 1 fault, in that case it can uncover that. This can also, so now here if I use this 4n test, the March M0 is so there are multiple tests. I'll come back. This first test that I told you is called as MATS, marching algorithm. That is, in first you are writing 0 in all cells, then you read 0 and write 1 in the say increasing order of addressing, and then you read the value stored in that in the reverse order of March M1. And now the complexity of this one is say 4n. This can cover all stuck at 0 faults, all stuck at 1 faults, right? That we can evident from this state machine. Both of them, I mean, we can distinguish this state machine and this state machine and this state machine and this state machine easily. This can also cover some of the transition faults, but not all. Which transition faults it can cover? Because I mean, what we are doing, we are writing, see, first 0, then we are reading 0, we are writing 1 and reading 1 here. and all of these, if they are correct, in that case we can say that this cover this won't have stuck at 0 fault, stuck at 1 fault. But it covers some of the transition fault. Which transition faults it can cover? Can cover when so I can ascertain that this has value 0, this has value 1, and after having the writing the value 0, and I am able to create this transition W1, right? I can create this transition W1, and in the W, after creation of the W1 transition, I can also observe the state at the end. Now when I can observe the state at the end, in that case, now the good machine must have this behavior, and bad machine, when there is a transition, I mean, this is like here, there this is stay with the logic 0, and therefore this would be a bad machine, and this particular we can distinguish between this machine and this one machine, right? And therefore this can detect this transition fault 0 to 1. However, this cannot detect the transition fault 1 to 0, because the machine will have the good machine will have this transition that go, I mean, even bad machine will have this transition as 0 to I mean, on getting W1 it will go to S1. However, this transition will fold over here, and because I'm not reading that after that operation, in that case that transition fault cannot be detected. Perhaps you can give a thinking about it. So this MATS test that we can have maybe can detect all the stuck at faults. Sorry, I'll go back. Yeah, this can detect all these stuck at faults, stuck at 0, stuck at 1. It can also detect the transition fault that goes from I mean, transition from 0 to 1. However, this won't detect the transition fault from 1 to 0. If I change the sequence, if I make this as first W1, then R1 W0 and R0. In that case, it can detect every stuck at fault and transition from 1 to 0, but this won't be able to test the transition from 0 to 1. So the and the complexity of this is 4n. That means I need to do 4 operations with every cell, and so this is how we can develop a test that is feasible to be applied in a given amount of time. We try to make use of the limited functionality of these kind of devices, and can looking at the functionality of the device, we can make a a simple functional model, and based on the simple functional model we can develop the fault model. Those fault models we have used here are the stuck at fault model, transition fault model, coupling fault model, and then the pattern sensitive fault model. So these are the four say reduced fault model we developed, and we have developed at least one test so far, that is that goes through the three marches: March M0, March M1, March M2. In March M0 we are writing everywhere value 0. In March M1 we are first reading the value of that particular cell and writing the value 1. And in March M2, in the reverse order of March M1 we proceed, and then read the value of that particular cell and check against whether that value is 1 or not. And in this one we can uncover all the stacked faults, or the sum of the transition delay faults. So I stopped here today. We will continue with this one in the next class, and maybe then it has some relationship with the built-in self-test. So again we can revisit this one much bit later. So the other test, they are much simpler one once you understand this maths test. W0, writing the three marches, M0, M1, M2, and why I need to follow some sequence. Keep in mind always that we want to distinguish these machines. This machine for stick at model between the machine this one and machine this one, and or the machine this good machine and this machine of stick at one. And for the uh, say transition delay, I mean transition model, fault model, I want to distinguish from this is good machine to the another faulty machine over here. And those 4n kind of tests are good enough to test. So if I have say 1 billion or say 1 million element in the memory, in that case you need to have 4 million read and write operations, and you can compute the time needed for 4 million read and write operations. That's the time it will consume. Maybe I stop here. Maybe in the next class we will take that forward. Thank you.
So much, sir, for your insightful talk. It is really interesting. I hope all the students have actively participated. There is one question in the chat box, sir. You were talking about the March test. So there were different March like M0, M1, M2, M3 like that. So one of the student is asking why we are going to rewrite at M2, we are rewriting 0 while we wrote M0 as 0. So during M0, March 0, we have written 0. Then again after M1, M2, we are again writing 0. So he's
So
asking questions.
I mean, I have not discussed this one. There is a reason. I'll come to that point in the next class. Here, for that's what I said many times. Forget about this W0. Consider this maths test as W0, R0, W1, and R1. This gives me this can test the all I mean stacked faults and some transition faults.
Thank you so much, sir.
So
So
that
audience,
that is not needed, and for everything there is a purpose.
yes, sir. Thank you so much.
Now that test was augmented to the following test that I have shown over here. That is called as Maths Plus. That is now here we have added one additional step into that. That is called as Maths Plus. So this is 5n, 5 operations with every cell. Then it was augmented as Maths Plus Plus. That is like added one more say operation here. So in that case this becomes 6n and so on and so forth. So I'll discuss that here. Why what is the need, why I need to go for this. If once you digest this first maths test, which is fine to say uncover all the say stacked faults and a few transition faults.
Thank you
Thank
so much, sir, for the insightful lecture. So anybody else, if having any questions, you may type in the chat box. Otherwise, so we are going to conclude this session and we will start the next session. Or maybe you can compile your questions and in tomorrow's session you may ask, because the topic is going to continue tomorrow. So you may ask those questions to ma'am. Thank you so much. Thank you so much for the insightful lecture, sir. You have discussed different
Thank you.
kinds of faults and how to detect those faults using the
Th-
maths and other algorithms, sir. Their complexity and how it really matters to detect the fault with the help of mass test. Different faults will be tested. These things have been discussed today. So thank you so much, sir, for your insightful lecture. And yeah, we
Thank
will
you.
be, the participants will be waiting for tomorrow's session, sir. Thank you, sir. So, dear participants, now we will have a little bit a break because we need to switch the session. So, let's have a break of 7 to 10 minutes, then we will rejoin. Thank you.
Okay, thank you. I'm now signing off.
Yes, sir. Thank you so much, sir. Thank you. Gaurav, please change the session. Yeah, please change the session. And let's start in by 11:32. We are going to start it again.
Okay. Yes. Okay, yes. Thank you. Okay, yes, ma'am.